going to share and talk about nanocrystal electronics. And of course, like many of us, I'll start by thanking all of my students. Many of these are former, a few faces who are still at Penn and responsible for the work that I'll share. And well, we're hoping to get to take a new group photo one day soon. But many of the newer students who have come who are not yet in the group photo. So, and with that, I'll just thank also, of course, we always thank the agencies that have supported the work that I'll share with you here in the US from the National Science Foundation and our Office of Naval Research. And then much of the work that I'll tell you about today, we have a strong collaboration with the Murray Group at Penn. So you'll see lots of that in the acknowledgements of the work that's been done. So I'll start and just give you a little bit of a roadmap as an outline of what I'll describe today, and also in the context in particular about thinking about electronic devices. So of course, our first step for all of us on the device side starts with the synthesis of the quantum dots or nanocrystals. So I won't talk about much of that today, because I think you've heard lots about the synthesis of nanocrystals. I'll talk about systems that are capped by, of course, starting with the organic ligands used in synthesis, how we create inks. You saw this also in Professor Loy's presentation, lots of vials of dispersed quantum dots. And then we use techniques similar today. I won't focus so much on the assembly techniques, but where we'll mostly use things like spin coating. But what I will focus on is thinking about, from an electronics perspective, the importance of things like ligand exchange and approaches for doping. I think this actually came out in the questions from Professor Loy, examples where we have sort of glassy or locally ordered assemblies of quantum dots. I'll also get at the end to things where we have ordered arrays and some of the systems where we start to get these, where we can make these epitaxial fused structures. I'll talk a little bit about the transport in these different materials and how do we manipulate them ultimately as part of thinking about engineering devices. And so I'll talk again, and you'll see some commonalities between, of course, what's broadly important in devices, whether it's electronics, which I'll focus on, or some similarities that Professor Loy spoke about in photovoltaics. But we'll talk about some of the device engineering that's important and impacts the performance. And then once you can make devices, how we go about taking them and integrating them into circuits. This is an example of a 4-inch piece of plastic with many different circuit topologies. I promise to introduce you to circuits. And then I'll talk a little bit approaches about in our foray into making and thinking about more from a manufacturing standpoint, the opportunities to sort of take advantage of these solution-based materials as a way to start building devices entirely from solution-based materials and nanocrystals. Just to start, I think you've seen lots of these examples already, so I really won't speak very much here, but of course I said the first step is in synthesis. So in all of the examples that you'll see today that I'll share with you, the colloidal nanocrystals are all synthesized using wet chemical organic phase synthetic reactions. So like the ones that you'll have seen throughout the school, ones where the particles will all typically be small and capped with originally from their synthesis pot organic ligands. And of course, these structures will then, most all of the things that I'll talk about today will be particles that are small enough in size that they are quantum confined, and are the examples you'll probably have seen throughout the discussions where, and the part I'll focus on just here for a moment, I'm sure you've seen lots of different vials with different colors that come simply by tuning size. The community has done such a great job in developing synthesis for materials with band gaps that are tunable through the UV, the visible, and into the infrared. As you can see here as a plot, this is one from the Reese group. This photo here is from the Krauss group at the University of Rochester. And some very old data from Chris Murray's thesis. This is on cadmium selenide nanocrystals, and just showing what the absorption spectrum looks like as you tune with size. And you probably know this very well. And we think about it from a standpoint of a particle in a box. And so if you're comfortable with energy as a function of distance, which is what this is here, and thinking about what quantum confinement is, and thinking about these as sort of conduction and valence band states, or HOMO and LUMO. I'll try and mix my choice of language to make it accessible to everyone with different backgrounds. But you can see that these states can either be looked at energy versus physical distance, or energy versus crystal momentum, or K, if you're from the semiconductor community, where in here, the blue here is showing the bulk E versus K diagram. This would be the bulk bottom of the conduction and valence band as well. But you can see if you drew lines that this green line should align with that green dot, and so on. So you're just looking at where those quantum confined states are. And mostly for today, I'm going to use these diagrams, both of them, as building blocks to sort of tell the story about what the electronic structure looks like in assemblies of quantum dots, and why that's important, of course, in affecting transport through these materials, and ultimately in realizing their devices. So here's the sort of building blocks that I wanted to, I'm going to try and do this in a sort of stepwise fashion, that if we look at the energy versus distance diagram here, right here, the quantum confined states that are characteristic of the core of the quantum dot, and the shell is just drawn in as some ligand shell here in blue. That's and you can see, of course, that as we know from quantum confinement effects, as we make the particles smaller, we increase the effective band gap of the nanocrystal. And so that's what we saw in the last slide. And now the question is, well, what happens if we start making assemblies of these? And so if we add, take one, we add another, then we add lots of them, which is what we do, for example, in assemblies that we deposit. And so that ultimately we make arrays of these nanocrystals. And if all of these nanocrystals were perfectly identical one to the other, which meant that there was no size distribution, no variation in their surface chemistry, anything that would cause nothing that would cause an inhomogeneity in the energy of those states. So there are lots of things that can do that and influence them. But if they didn't, and they all had the same energy level, then as you bring these together in an assembly, I've kind of drawn here in this energy diagram what a superlattice might look like. And I think Professor Loy mentioned this idea of bands or mini bands that might form between these systems. With the original ligands that are on the surface of the nanocrystals, they sort of maintain a separation between those nanocrystals. For many of the ligands that are used in synthesis, this distance of separation between the particles is something on the order of 1 to 2 nanometers. So in general, we would say that when we start to bring these together here in these assemblies, we would call them as sort of weakly coupled. And so you can see effects that are a little bit longer range, things like energy transfer phenomena, but it tends to be that charge transport is not very good in these assemblies. And so that as a community, and you saw this as well in Professor Loy's presentation as well, is that whether we're making electronic devices or optoelectronic devices, what we typically do is to exchange these ligands here with something that's shorter. That could be, and I'll give you a little bit of a library in just a moment, but that could be a shorter organic ligand or one of these compact inorganic ligands or ions. And so as we do this, if we bring these much closer together, then the wave function on neighboring nanocrystals overlap, and these energy states will start to broaden. And so you might expect that the bandwidths of these mini bands would broaden as well. And so that's very much classic. Professor Loy chose to show their sort of coordination diagram on her slides, very much the same picture, very much that from atoms as you take isolated atoms and you bring them closer together. Of course, when we have lots of them, that's how we talk about having bands where the difference between energy levels that are contributing are small, so effectively they look like bands. So in this top diagram, this is a very idealized case where all the quantum dots energetically look the same. They have the same effective band gap and they have the same energy levels. And you can see that here within my ability to draw in PowerPoint, they all have these are all nicely lined up. And then of course the energy levels are the same. So what happens in a real system, and that's very much important to us as experimentally and thinking about what the materials and ultimately the structures look like. And so on the bottom here, I'm showing you, what we might expect, that as you've heard, we've gotten, as a community, we're very good at making quantum dots, but there's still some residual, mostly from size distribution, but inhomogeneity in their energy levels. And so this is really just meant to be a schematic, just to show, there are some variations. If you look at the bottom of the positions of these structures, they also get some variations in these systems. And that's true in the conduction and valence band. It means that these energy levels will be a little bit offset. They can also be offset by influences actually just of surface chemistry, which will change actually the absolute position of them as well. And then as you look at these structures, one of the things that we also have in real systems, which I've shown in orange, is that you can have states that come often from the surface of uncoordinated atoms at the surface of the particles that introduce states within the gap of the quantum dot of the semiconductor. And as we've seen, of course, those are so important in solar cells, and they will also affect transport. It may depend on exactly where these energy levels are in terms of how influential they are on different types of devices, but they're important for us in developing and looking at the applications of quantum dots in devices. So if these are far apart from one another, you can imagine that as you have in the original ligand, that you just get sort of a representation of all the states of all of the dots that are in your ensemble. And so that will give you sort of that inhomogeneous broadening. But as you bring them closer together, you can imagine again that if you couple them very strongly, the bandwidths will eventually be large, or could be large. And the question is how much do these broaden in comparison to the variation that you get in the individual energy levels of the system? So in this case, in this depiction here, the idea is that it broadens enough to overcome this variation in the position of the energy levels of the individual particles. And often, to be honest, as we explore some of these ligand chemistries that I'll talk about, and you saw in Professor Lloyd's talk, as we do that, often we introduce additional defect states as we take things off and put them on the surface of the particles. So perhaps we have a system that looks more like this, maybe not even quite, depends on what the bandwidth looks like, but in a real system. But that's just to give you an idea of how important it is to look at the distribution of the individual particles in terms of their energy levels, the importance of controlling their surface chemistry as a way to both control distance as well as to passivate surface electronic states. So I thought I'd tell you just a little bit more and present the flip side. Instead of showing energy versus distance, I would show you this same story in thinking about the energy versus crystal momentum or wave vector. So this is the same plot from the previous slide. And if you look at this example here, just to give you a real space image of what we're talking about, is that in this upper left-hand side is an electron micrograph of, this happens to be 6 nanometer lead selenide nanocrystals capped with oleic acid. And so you can see that if you look at the nanocrystals that appear dark, any of the lighter contrast, right, is really showing you that physical separation between the particles, which for oleic acid is usually on the order of about 2 nanometers. And so, in fact, when long time ago, I'm trying to have to think what this is, 25 to 30 years ago, when I first tried to do DC transport measurement, and I talked to one of the physicists, and he just thought, who's a guy named Mark Kastner, who's very well known in transport physics, and he just thought these were the most insulating kinds of, these materials were so insulating. And that's really a measure that if we want to think about using them, it's why the community that you see for all sorts of devices looks at replacing these ligands with something smaller. So you can see this is an example where we took a sample that looked like this. This is actually, and we were to do ligand exchange. We can exchange the ligands. In this case, one that we've liked in our group is thiocyanate, although there are lots of good ligand chemistries. And what you can see is that when you expose this sample to thiocyanate, you can see that you reduce the distance even to the point where you can start in some compositions, you'll start to even see them neck and fuse, especially if they have a very simple crystal structure like lead selenide does. So if you ask, well, what does it look like? So again, I'm just insetting here the two pictures that I showed you on the previous slide of a real sample with long ligands with something as short ligands. And what you should expect is that all of these energy levels that represent the inhomogeneous distribution, you can see if I focus on the lowest sort of 1SE and 1S and highest 1SH state in the conduction and valence band, that these effectively are broadened by the inhomogeneous distribution, but they're not, the strength of interaction is often not that strong, right? We said that they sort of weakly couple. So this broadening is actually from a real sample that we measured optically, but just to give you a sense of what it looks like. And then you can, as I showed before, you can have states like this, and I've just drawn this in as a schematic, that you can have states that are in the middle of the gap, for example, that come from example, different defects or dangling bonds at the surface. They can also have band tail states, whether from the conduction or valence band. These surfaces, when we think about them ultimately in devices, these states can come from the nanocrystal surface, or as I'll try and show you today, is that it's also influenced by the surface between nanocrystals and various device interfaces. So I'll show that to you, for example, in the example of electronic devices today. And then, of course, as we do this ligand exchange process, what we said is that we expect these to broaden, and this is also originates from some experiments some long time ago in optical absorption measurements, where we often then see that these states will broaden. We're bringing these particles closer together, which not perhaps well represented in my schematic is that the density of these states will grow just as the number of particles grow. As you see here, right, you can still have, these states within the band gap. And so that's sort of the picture of where we're starting as we think about looking at what the electronic structure is of these nanocrystal assemblies when we integrate them into devices. And you'll see that a little bit more because it'll ultimately affect their transport characteristics and the mobility of field effect transistors. So just to go just one step further on the ligand exchange, you saw some of these examples already today, but I'll just share with you as a sort of reference is that you can have, there are lots of different ligands that are being explored in the community. Many of the ones that are used in synthesis are kind of in the middle here box, where we're using carboxylic acids, phosphonic acids, sulfonic acids, phosphines, thiols, diamines. Depends on their size, but often they maintain a sort of 1 to 2 nanometer distance between the particles. And then often to get this sort of much more stronger coupling, I know this came out in a question between, unfortunately conjugated organic molecules still have a decay function as a function of distance. And so, as Sergio said, it was better to have nothing than to have those even conjugated organic ligands. And so we do see that many of the ligands, this is an example of a number of the ligands that have been explored by our community. There's a very nice review paper by Taewon Hyun and Dmitry Chalapin. We've also covered some of this in our review papers, but you can see that we can use these chemistries to really bring the particles much closer together, where you get sort of stronger, what's known as exchange interactions between the wave functions of electrons in different particles. I won't talk about it today, but just for completeness, there are ligands that can be longer and push in the other direction. And so for not so much for electronic devices, but in some other, for example, optical devices, it may be interesting to maintain a larger separation. And so there are lots of different dendrimers and polymers that are being explored to put those on the surface of nanocrystals that'll maintain a much larger separation. So this is for completeness. And I just wanted to give you an example of what you see. So Professor Lloyd also introduced these ideas of if you make, you can approach this idea of changing the surface chemistry in one of two ways. One is often referred to as solid exchange. So if you make an assembly of nanocrystals like you see here, you can simply take this, and actually this particular picture was a video we had, snapshots from a video we had made, but this is, we actually put silver nanocrystals onto a piece of plastic substrate. And you can see that if you measure them and you take your multimeter, you look at it and it just pins out that these are highly resistive materials. But if you immerse it into a solution of one of these compact ligands, and so this is an example of thiocyanate, this was immersed for 30 seconds. And then afterwards, you can measure it and it now becomes much more conductive. In fact, you can make metals nearly as conductive as bulk thin films. The other approach is, instead of putting down the film and then replacing the ligand, is that for some chemistries, the communities develop routes that allow you to exchange the ligand while the particles are still dispersed. It's a little bit more challenging than when they're already on the surface, as in solid exchange, because the replacement ligand has to still be able to then maintain a dispersion. But this is an example. Also, if you look on the left-hand side, this is a biphasic solution where you have cadmium selenide nanocrystals with their original phosphine oxide ligands. And so they like to be dispersed, for example, in a nonpolar solvent like hexane. It happens to be layered with dimethyl sulfoxide. So you see they truly phase separate. If you take these nanocrystals and you replace them, for example, this happens to be for thiocyanate. If you replace it for one of these compact ligands that tend to have more charge, then instead of being dispersed in the hexane phase, they can be dispersed in a more polar solvent like dimethyl sulfoxide, dimethyl formamide. There's a host of that, formamide, a whole host of those kind of chemistries. And so you can do the ligand exchange first, and then you can, this is just showing, you could spin coat them onto surfaces. You can do all the things in controlling, for example, concentration and spin speed. And this shows you can just, for example, tailor the thickness of a deposited film already that has been exchanged with thiocyanate. So for a lot of the examples, when I show you cadmium selenide today, we'll actually use this process here of solution exchange. And the reason is that there's an advantage that, of course, if you have to replace the ligand once it's deposited on the surface, everything comes together and you get shrinkage and often cracks. And so, for example, even in the examples of the solar cells, often as a community, we deposit one layer on top of the other as a way to also infill that space. You don't have to do that so much in this case here, where you do solution exchange. There, you don't have that volume change. And so you'll see, as I described shortly, for the example of transistors or electronics, often we only care about having a thin film. So it's nice to have an example that doesn't require that sort of sequential deposition. So now, if we sort of, one prerequisite to actually getting transport I showed you in the last slide is that, well, we got to take these particles, replace their ligands, and bring them much closer together. But as you know from conventional or bulk semiconductors, we also like to control how many carriers, the carrier type. Is it electrons or holes? Is it, how many do we have? And the interesting thing for these kinds of materials, as well as, when we teach device physics in class, right, we teach about a perfect single crystal. But whether you have a polycrystalline film, an amorphous film, nanocrystalline films, of course, the density of states, like I showed you before, looks much more like the depiction here. So there's a lot of similarities between nanocrystal films and sort of amorphous or films, even of atomic systems. And so what happens is you see some sort of band tail. It's often referred to as a mobility edge, and a tail that extends into the gap. And so you tend to see these systems here like this. And so what does that mean is that, in a perfect single crystal, any electron that you put into the system goes into the conduction band, right? Because there would be no states in the band gap. But in an amorphous system, for example, if you have states in the band gap, then the Fermi level tells you how you populate those states. And since there are states here, you can put charge into the states within the band gap. And so it's very important, as you look at this, to think about how do we, in fact, that as we look at not just carrier type and concentration, but depending upon where the carriers are, will affect how large the mobility is for transport in these films. So for example, if you don't dope your nanocrystal film and your Fermi energy is, for example, here near the middle of the gap, and you draw yourself a picture of the Fermi-Dirac distribution, it'll tell you that you'll have lots of occupancy of charge here and perhaps not so much in these higher states. And so what we'll see is that the transport and the mobility will be low. However, if you dope these materials, for example, and you push the Fermi energy up closer to these higher density conduction band states, or the 1SE states of the nanocrystals in the assembly, and you would look, now you start to populate these higher density states, and they're also of higher mobility. The sort of more dense they are, the broader the bandwidth, the higher the mobility that you get. So actually doping is very important, and that doping can be approached by chemically, for example, like we know in a bulk semiconductor. In bulk semiconductors, we typically talk about substitutional doping, where we sort of take one atom out and put one atom in its place in the core. Lots of work in the community to do that, but it tends to actually be harder to do that during synthesis, even though there's some beautiful work and advances by the community to do that. So today I'm going to talk to you about a little bit different approach. I just want to say that I won't talk. There have also been nice work on electrochemical doping. For example, Philippe Guillaume-Sionne's group has done some nice work looking at electrochemistry. From a standpoint of a solid state device, we don't typically want the liquid around. So I'm going to focus on either chemical doping, or in the architecture of the transistor, I'll introduce you to the idea that electrostatically we control carrier concentration. So in nanocrystals, instead of just doping in the core, which has been a little harder, most of the approaches that we've taken is instead to dope, but that tend to put atoms or ions or ligands at the surface that ultimately then transfer their charge and control the carrier type and concentration in a nanocrystal assembly. And so if you look here on the right-hand side, lots of the ligands can influence. You saw this in Professor Loy's talk, which said, well, the iodides tend to make them more N-type, and that's true. And so ligands can control and affect the carrier type and concentration in an assembly of nanocrystals. We also found, so I'll show you this particular work is from the Talapin group that first looked a lot at this ligand engineering approach, introducing some of these cockaginal dimetallites. And then, for example, back in 2013, we had looked at using using evaporation. I'll show you that. Actually, that was even beforehand. But this is an example too, where we could show we could make the lead cockagenide systems N-type or P-type. Actually, we really did the experimental work on showing the control of stoichiometry as a way to control carrier type and concentration, much like you saw from Professor Loy. And then not only can you use sort of evaporation in metals, which is sort of a physical vapor deposition process, right? You use an evaporator, but also the idea that you can use sort of consistent with the approach of handling things using solution-based methods. We looked at what we consider a sort of post-synthesis colloidal atomic layer deposition process. And it has its analogy in approaches that people develop, whether they call it SILAR, or they also use colloidal atomic layer deposition for approaches while the particles were still in the synthesis pot. But what we saw is that if you, you saw this also in Professor Loy's talk, that if you take this is an example of like cockagenide nanocrystals, and if you were to use and just dip them in metal salt solutions, for example, you can introduce more chalcogen, and you can actually see quantitatively through analytical measurements that those chalcogens will bind to, for example, to surface lead, and then you can enrich it in the chalcogen, which, as you saw before, that'll make it more P-type. It'll introduce more holes. And then if you expose this to a lead halide solution, for example, the lead will bind to surface chalcogens and then add to the surface, and then you can, you change the stoichiometry and you change the carrier type and concentration. So you can use all of these approaches. For example, and I'm going to focus, I'll try and introduce examples that you see of all of these approaches in electronics, either using ligands or aliovalent, we tend to talk about them as impurities, or isovalent atoms or ions that either provide impurities like we know more conventionally from doping of bulk semiconductors, Or even in bulk semiconductors, people had studied back in the 1970s that if you alter stoichiometry, you will also alter carrier type and concentration. So the key point that I'll have you, I'm going to show you shortly, I'm going to introduce you to the transistor and then show you examples, but I'll have you watch and you'll see shortly that I'm going to show you that as you control the Fermi energy by approaches like doping, and ask you to remember that this picture here, that's important to occupying these higher density, higher mobility states. Okay, so first I thought I should give you an introduction to the transistor and everything that we learn in case you're unfamiliar with how it operates. So if you look at, this is a depiction or schematic of the thin film transistor. It doesn't matter, you can take this transistor and flip it 90 degrees, 180 degrees, however you think about looking at it, as long as the elements are the same, they actually operate quite in the same way. So there'll be some substrate. Sometimes the substrate also serves as the gate electrode when we use, for example, a highly doped silicon substrate. It could be a piece of glass, plastic, whatever, that really serves as a substrate, and you have a metal electrode. Either of those is fine, very similar. The key to the transistor is that in a field effect, we have an insulator that is spaced between the gate electrode and here, which I'm depicting, which is a nanocrystal film. And then, of course, you have two electrodes on the left and the right. These are known as the source and the drain. This is known as the gate electrode. And so you'll see, and what I'll describe shortly, is that often we think about this source electrode being the ground or reference, and that we apply a voltage to the drain electrode. And if you ignore everything else below here, you would think of this as basically a resistor, right? And this is the conduction path from left to right, from the source to the drain. Sometimes I make the analogy, it looks like, if you were at your faucet and water was pouring, right? You'd see it going from the source, which is your faucet, to the drain in the sink. And the key is that the gate is like the valve on the side of the faucet, that as you change the voltage on the gate, and actually this in this case should have extended all the way to here. As you change the voltage on the gate, then that acts to modulate the carrier concentration like you control the flow of water, and that controls, therefore, the conduction from source to drain. So there are a couple of things. So this is what I mean by electrostatic modulation, in the sense that when you apply a voltage to this gate, you can look at this, it'll look like a metal insulator, metal capacitor kind of structure. And so I'll show you that as you apply a voltage here, then you're going to get sort of the opposite polarity of charge in this channel here. So I'm going to show you that in just a moment, and just highlight that, coming back to this idea that you only need a very thin film in nanocrystal to make a transistor. In fact, you can make a transistor out of just a monolayer. Now, of course, you'd like a nice uniform monolayer of nanocrystals. You can also do this with molecules, all sorts of different semiconductor species, but you really need just a small thin layer in order that's going to get influenced by the potential that you apply to the gate. So all the action is here, which also means that this interface here between the semiconductor nanocrystals and the insulator is very important. All right, so how does this work? So I'm going to show you this in animation. So if you were to look and you had no voltage here applied to your gate and no carriers here in your semiconductor channel, that if you applied a voltage on your drain relative to your source and there are no carriers, there's nothing to transport, right? And you get no current. So if you look at the current versus the drain voltage, when this gate voltage here is 0, you get no current between the two. But if you were to increase the gate bias, for example, and if I apply a positive bias to the gate, then on the other side, if it's a capacitor, I get the opposite polarity of charge. For example, I get electrons here. And now if I looked at the voltage between source and drain, then you could see, I would see an increase here in the current level. And if I keep changing the voltage on the gate, I'm going to get more charge, more current, more charge, more current, and I get a whole family of curves. That's what you typically see when you think about what the sort of characteristics are of a field effect transistor. Now, when we make thin film transistors, we're typically, for anyone who knows transistors, we're typically operating in what's known as an accumulation regime. Oops, sorry. we're operating in an accumulation regime in which the carrier type is, or what the nanocrystal layer is willing to transport, we're just accumulating more of those carriers. So often in a sample that is already a good electron transport material, if we apply a voltage that increases the electron concentration, we'll get a greater transport of electrons in the material. So what we see here is that these are our classic current voltage characteristics as we sort of modulate that gate. And another way that we look at these, that where you think about it operating as a switch, is instead to look at the current voltage characteristics. Oops, sorry, I have to make sure I'm on the right thing. Is if I look at the current voltage characteristics at a fixed drain bias and then plot it instead as the current looking at the gate bias. So if you look here, I have this little dashed line down here on the left. That's at very low voltages, like 1/10 of a volt. And what it's very hard to see because they're all very at a much lower magnitude than the absolute scale here. So I'll highlight, this is not in this region here is known as the saturation regime. I'll explain that in just a second, but you can see that below 0 volts, right, we have very little current like you see here. And as we come up above 0 volts on the gate, you start to see the current get bigger, 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 and bigger, which is what you see here in the purple plot. And I'll just show you in this particular example, I'm showing this to you on a log scale. And the reason for that is that if you think about a switch that goes between 0, in an ideal switch, it would increase infinitely fast. And I'll describe that in a moment. And then you reach this sort of on state here at high voltages. And the nice thing, and the reason for showing it on the log scale, is that you really want to have many orders of magnitude to differentiate between the off state and the on state of the device. And so that's why I showed you this here, where we get more than 6 orders of magnitude in modulation between the off and the on state. And this happens to be a cadmium selenide nanocrystal transistor. The reason, by the way, that this is called the linear regime is that if you look in this region here, all of these characteristics are in fact linear. And they're just, you know, and it comes back to thinking about this as a resistor here, which would have linear current voltage characteristics. What happens is as you push the voltage higher on the drain, then this drain bias affects the carriers here locally. And so at some point there, it's something that's known as pinch off. I won't go to it in that detail here, but that then you sort of get a saturation in how the carriers can flow through this region, and they sort of level off and hit this, what's known as saturation. For the point of today, what I want to do is I'll show you now in the next slide, is that we can learn a lot from these device characteristics. We care about them from their operation in devices, the mobility, we'll call it a field effect mobility because it's measured here in the architecture of the transistor. We care about the on to off currents. We want this to be large, so it's a good switch. We care about threshold voltage when the device really turns on. How fast this rises is something called the subthreshold slope, and we can learn a lot about the shape. And it's all related to some of the transport characteristics and physical characteristics of the nanocrystal film. So I'm going to take that and sort of unpack that for you in the next slide. So this is just a repeat from the previous slide of just showing you the architecture of the transistor. I've put in a few other little characteristics so that you understand where the equations come from the transistor. And I've shown here, this is just a repeat of the previous current voltage characteristics. And in the one on the bottom, for the voltage at 1/10 of a volt, right, down here, where I said you're in the linear regime, instead of just plotting it on a log scale, I'm also plotting it, if you look at the right-hand axis, you'll see that I'm plotting this on a linear scale as well. And now I'm going to show you how you use these device characteristics and the architecture of the transistor to use it as a platform to understand charge transport. So these equations here are the characteristic equations of a field effect transistor in what's known as the linear regime and the saturation regime. They're the same ones that you would learn in device physics class for bulk conventional devices. We treat to a good extent all sort of less conventional semiconductors in the same way in transistors. So if you just look, I'll just point you to that when we talk about length here, this is the channel length, which is always the distance between the source and the drain. So I've labeled that L here. The width of the transistor is labeled Z. And so that goes in this direction. Actually, in fact, often Z is greater than L, so it's not quite the geometry that you think about from a conventional rectangle, but that's true here. And then this is the capacitance of the oxide. If you look at this as a parallel plate capacitor, you'll know that it depends on the thickness of the oxide as well as its dielectric constant. And I'll come to that. You'll see some of that play out in future slides. So that's what's in these equations. And so this is the current that you get between the source and the drain as a function of both the drain voltage and the gate voltage. VT here is this threshold or turn-on voltage for the device. So what you look at here is that often, if I'm looking at it in the linear regime where the voltage is really small, like 1/10 of a volt, most of the gate biases in comparison to the threshold voltage are much larger than this 1/10 of a volt. So you can often think about this contribution here as being small. And so if you ignore that piece, I just want to give you this sense that it operates much like a resistor, sort of variable resistor does. So this is just to show you, if I look at and sort of set your mind in thinking about things that you might already know, right? You know Ohm's law, which just says voltage equals current times resistance. So if I flip that around, and then I can say current is voltage over resistance. And then you know resistance depends on the resistivity, or inversely the conductivity of the material. And then it depends on geometric parameters like the length as well as the area of the film. And then if I look and ask what's conductivity, well, that just depends on mobility and the carrier concentration. And so if I look at this and I start with Ohm's law, you can start to see where this equation comes from, because the key here in a field effect transistor is that this carrier concentration is modulated, as you saw in my sort of animation, that as I change the gate bias, I'm going to introduce more carriers. And so, or if you know the equation for a capacitor, you know that charge equals capacitance times voltage. So here it's really looking at thinking about the carrier concentration. This voltage is now how much above threshold that I start to introduce charge. And so if I plug this in for the carrier concentration, you'll get an equation here that looks very reminiscent of the one that you see for the transistor. Minus this one-dimensional term, because we're really thinking about a thin two-dimensional layer that happens in carrier within a sheet and not through a volume here in the transistor. So that's what the characteristics, if I think about in the linear regime, it really is operating like a variable resistor. As I tune the gate bias, I'm tuning the resistance and therefore the current. And in saturation, what happens in saturation is that when this drain bias gets large enough to be as large as the difference between the gate and the threshold, that's the sort of onset point of saturation. And so mathematically, if you plug in VG minus VT for every place that you see VD here, then you get this equation here to describe saturation. And it's also something known sort of famously as the square law, because the current changes as the square of the voltage. So that's kind of the details of the transistor. I also want to show you what we learned from it. So if I look at these characteristics here, much like a resistor, I can think about how big the conductance is, which is just the slope of the current voltage characteristics at a given gate bias. And so if your device is working well and you don't have a limitation of injecting charge, that these source and drain electrodes really form ohmic contacts, then it'll be linear. I don't show it, I don't have it shown here, but if you don't, you'll sort of see this sort of sigmoidal shape where there's some barrier that comes from the contacts before you can inject charge. So it's always important in the transistor to engineer these device interfaces so you get good charge injection and nice linear increases in current. If you then ask, what else do I learn? So that's important for your device interfaces. I can also look, if I look at this red curve of the current versus gate bias on the linear regime, what you see is I'll introduce you to the term transconductance. And that's now the slope that you get in the current versus gate bias at some fixed drain bias. And this is in the linear regime. So we try and do this where the drain bias voltage is very small. So that's why I'm showing you something like 1/10 of a volt. And so if you look at this top equation here, if you take the derivative as a function of gate bias, then you're just left with this term here in front, this prefactor, which is what you see written here. And the key is that you know all the geometric parameters of Z and L. You know the drain bias. You know the capacitance of the oxide because you choose the oxide and its thickness. And so using the transconductance, you can get the mobility of transport in the field effect transistor. And so this is something that really allows us to learn about charge transport in our nanocrystal films. If we go further, I'll introduce you to this, the inverse of this, what's this called the subthreshold slope. And so what this SS stands for subthreshold slope. It's really taking this current versus voltage on this log scale here and getting the slope of this. The easy way to think about this is that if it was a perfect switch, the switch would, rise infinitely fast. And so if we take the inverse would be 0. So we like this inverse of this, or what we call the subthreshold slope, to be very small, to be approaching 0. Now, in electronic devices, there are limitations thermodynamically to controlling carriers, which I won't describe. But even in the best silicon transistor, you can't do better than log 10 kT over Q. And you can tend to make it worse. What does worse mean is that if there are different types of other capacitances that, for example, come from charge traps that store charge, then it will also add to and ultimately make this slope here more shallow. And so what you can see is that from this slope, we can learn about how large the interface trap density is between the nanocrystal film and the insulator that we use in our transistor, which is often an oxide, which is why I keep drawing oxide. So I'll show you that and how it plays out importantly in our design of devices and our selection of device interfaces. And then finally, the intercept of this blue curve here down to the axis tells us what's known as our threshold voltage, sort of where does the current in the current voltage characteristics turn on. And so if we dope something and we have more carriers, then you'll see that this threshold voltage will shift and it'll turn on sooner. And so we learn from this threshold voltage, we can use it as a way to study how we dope these nanocrystal films. Of course, if we also dope the films, it'll also affect the off current in these devices, because the more charge that you have by doping, then you'll already have a path for carriers to transport. So there's some opportunities that we look at that we can learn from the characteristics to understand transport. And then, of course, all of these metrics are device metrics that are important for their performance. So I'll also introduce this current modulation between the on and the off state. All right, so that was sort of the big detailed physics. And now I'm going to show you some examples and show you how it plays out in our design. All right, so if this is an example of a cadmium selenide nanocrystal transistor, if you look at the characteristics, you'll see that if I just take a nanocrystal film of cadmium selenide, this happens to be exchanged with that compact thiocyanate, and I just use aluminum electrodes here. We haven't done anything in particular to dope these materials. So even though we have these higher density of states by bringing the particles close together, you'll see that we have kind of okay, but not great currents, and the mobility for transport is low, on the order of 0.1 centimeter squared per volt second. And some of the examples using even longer ligands, like the organic ligands, you even saw in Professor Loy's talk, mobilities could be smaller, 10 to the minus 3 centimeters squared per volt second. So how do you make it larger? Well, one of the things that we showed is that we introduced and used this approach of evaporating a metal. And in this case, we evaporated indium and layered it into the electrodes of the device. And then we annealed it to allow diffusion of the metal through the nanocrystal film, which you can show analytically. But once you do that and you dope the film, now you can increase the current by orders of magnitude. And it's starting to look like a much nicer looking transistor. you also increase the mobility by about 250 times. So it really makes a difference to shift that Fermi level to get it into that higher density of states. And then, but if you look at engineering the interfaces, one thing is that if SiO2 has a lot of surface hydroxyl groups, it's broadly known in lots of thin film semiconductors to act as electron traps. So what we did is we layered a layer of aluminum oxide on top, which has a smaller number of trap states. And then you can see that by doing that, you can further improve the current and the mobility. And you can also see that this curve here in blue is sharper because you change that. You reduce that NIT, that interface trap density, and increase your subthreshold slope. So you saw something similar to this in Professor Loy's work. We had shown previously that you could take and use these same kind of approaches. I'll focus a lot as we go into circuits on cadmium selenide, because that one serves as has a really nice current modulation, which is something that we really care about for transistors. But in using the transistor as a platform for studying transport, you can look at these effects of, treating the surface, for example, with chalcogen, makes it p-type and very strongly p-type, degenerately doped. You can really use these approaches to shift the Fermi level all the way from the valence band to the conduction band by controlling, how much you dope your materials and with what you dope them. And so this is an example where you introduce the lead halide, you see it become less p-type, orange is ambipolar. And then if you add more, you can make it look like a better looking N-type transistor. And I'll just leave this without going, because I can see also the time, but just share in this review I had put together, you can see lots of different materials that have been explored in our community, anywhere from colloidal group 4, 3, 5, 2, 6, 4, 6, as well as I know there was one question on some of these sort of cadmium and lead-free materials. An example is in 136 materials as well that are being explored in devices. I also wanted just to share with you the idea that also the electrodes and ligands can be very influential on charge transport. So this is an example where we looked at the lead cacogenide materials. We looked at many of the different ligand chemistries that are explored by our community. These could be short organic ligands or these compact inorganic ligands. I have to admit, it really highlights the idea that less is more for a standpoint of charge transport. Where you can see if we expose ethane diethiol, regardless of what ligand we use, the resistance to transport in the channel is so high that they kind of all look the same, and the current levels are very small. And so it's really transport is limited by interparticle charge transport in these materials. But if you exchange it with some of these compact inorganic ligands, and I've highlighted the two in thiocyanate and something that tetrabutyl ammonium iodide, which introduces that iodide, which goes back to the example that the iodide tends to make things a little more N-type, which you can see because the currents are bigger here at higher gate biases. And then this is, for example, the thiocyanate. And so what you can see is that once you do this, now charge injection at the electrodes can make a bigger difference. So we looked at 5 different electrodes from aluminum to palladium. They're sorted by their work function, which varies from just over 3 electron volts to about 5 electron volts. And you can see that as you change the electrode, you can modulate the current voltage characteristics from something that looks more P for a high work function metal to, as you go to a lower work function metal, more N. And then in TBAI, because it likes to be more N-type, it's just a question of how N does it look? How many electrons? How efficient? So charge injection can also influence the carriers that are in the channel and ultimately the characteristics that you see. My concern about time, I'm actually going to skip the example of some of the low temperature transport measurements so that I get a chance to introduce you more to the circuits and thinking about how we get to the integration of the devices. So you can take these devices, and one of the things that we were very interested in doing first was how to get these materials on plastic. So you can use these same kinds of processes that we've described. Things like the thiocyanate chemistry is compatible with plastic. We tried hydrazine, and for some time it's very corrosive and ate our plastic, so that was not so good. But you can see that a couple of things that I want to point out here is while we study transport often in oxidized silicon wafers, the voltage ranges there were higher because of the thickness of the oxide. But you go back to these equations here and know that you can, if this is your carrier concentration, if you look at your oxide capacitance, if you increase the dielectric constant of the oxide or you reduce the thickness of the oxide, you can increase its capacitance, and therefore at a lower voltage, you can introduce more carriers. And that's how we scale the operation of transistors. That's sort of been this whole thing about scaling in part in Moore's law for years in semiconductors. We're just behind in nanocrystal materials. But as you do that, you can now make devices operate at much lower voltages, just a couple volts. And you can build them on plastic and get very similar characteristics of having devices that operate with relatively high mobilities. So how do you go from there and integrate them into circuits? So I'm going to show you the simplest one and introduce you into some of the physics of the circuits, and then I'll have to show you just some examples afterwards a little bit faster. But if you look here, this was our first attempt, and the one good thing about this is that it makes it easy for you to see. This is one where we first built circuits to show you could use colloidal nanocrystals, but we did it with shadow masks. This was a tour de force. My poor students had to very carefully overlay one layer and the other. But what you see is that in these circuits, what happens in circuits more generally is that in the transistor, you have a gate layer and you have your source and drain layer on top. And in circuits, the key is that you effectively connect different source and drain electrodes to different gate electrodes through what's known as a via. So somehow you have to connect the higher source and drain electrodes to the gate electrodes underneath. And so you have to create pathways or holes, things that are known as vias, vertical integrated access holes, to connect those. And the way that I like to think about this in circuits as an easy way to describe it is to think about it as two floors in a building that are connected by a staircase so that you can control the flow of charge. So in this case here, these are, if you look at this piece of plastic, there's one transistor here, there's another transistor here, and all of these other connections that you see, these four, are represented by this diagram. So this is the characteristic representation of a field effect transistor, where this is the gate, this is the source, and this is the drain. In this case here, we introduce something that's, all these devices I'm going to show you first are N-type. So we create something that's known as a saturated load. What it means is that we tie the gate electrode here to its drain electrode, so that it's always in saturation. It's always operating in the saturation regime, no matter what voltage you apply. This is the driver. It's known as the driver. It's another transistor, and then this is its source, its gate, and its drain. And what you can see here is that we can control the dimensions of these devices. And so you can see here, this one here looks really big, and this one here looks really small. And if you look at this direction and this direction. So as we look at that, we control their dimensions, which ultimately is important to its operation in the circuit. So this looks like just like the characteristics of the transistor that I showed you on the previous slide. This is, for example, here is the characteristic of the drive transistor. And what we're going to do is that you can see here that now at the drain is also the output voltage of this circuit. And if you look here, the gate is now the input voltage of the circuit. And what we do is that I'm now going to overlay it with this transistor that's always in saturation. So it kind of looks like those current voltage characteristics I showed you before. It's always at a voltage that puts it in the saturation regime. And so it's going to be low and then increase. And so the key here in the operation as a circuit is I'll introduce you to what is an inverter. So the inverter is how big this voltage out is. That's what's on the left-hand axis in comparison to the input voltage, which is the gate bias. And so what you do is that you look for the intersection of points between the load and the driver. So you sort of pick the intersection between the red curve and the black curve. Of course, in practice, we take many more points than I show you here. And so what you can see here is that when this input voltage is low, right, this is the gate bias. When that's low, this output voltage is high. And then as you look at the intersection here, you'll start to see that as I increase the output voltage, as I increase the input voltage here to 1.2, 1.6, and 1.2, you'll see that this output voltage is getting smaller. And so you could map that onto this curve here, which you can actually measure. So this is what the output voltage looks like as a function of input voltage. And the two key here is that this is where it operates as a switch. This is the output high, which is to say that your voltage output is high, and this is your output low, where the voltage is low. But the key to it operating as a switch is that when the input is, or as an inverter, is that when the input is high, the output is low, and vice versa. And in between, if I take the derivative of this curve, you'll see that it's small, it gets bigger, now it's fairly linear, and then it gets small again. And that's what's shown here in the blue curve. And it's a way to quantify what the gain is of the device. And so that's what's shown here. The gain is related to the dimensions. It's why we picked these dimensions. So we could design a device with a relatively, with a gain of our selection. So as I look at this, this is where the device gain will tell you that we're amplifying a signal. So that's how we use it as an amplifier. And then otherwise, in these other voltage regions, we can use it as a switch. So I know I'm running low on time. I'm going to try and just give you some examples here where if we put a small input voltage, which is shown in black, we can get it to increase by amplifying it in this nanocrystal circuit. We can measure it as a function of frequency. I'm going to kind of skip through this part because we're running low on time, but you can see here that we look at as we drive things at higher and higher frequencies, some of the other what are known as parasitics. But
Cherie, please, if you need a little bit more time, it's not a problem because we're gonna have the discussion afterwards.
Okay,
so
thank you, Sergio. I appreciate it.
Don't worry about it, okay?
I know I always worry in circuits that not many in the community work on them. So
it's all right. It's okay actually. Thank you. Please go ahead.
So if you look at this characteristics here, you'll see that the gain remains high, and you get to higher frequency, it drops off. And that's because there are other capacitances. If you look at these really big devices, what happens is that anywhere that the gate and the gate and the drain overlap, it creates an extra capacitance, and it limits the frequency at which we can drive our devices. So I'm going to show you in a moment how we can scale those devices and limit that overlap so that we can make these amplifiers operate to higher frequencies. If anyone's not used to this, dB is decibels. It's just taking this gain in blue and writing 20 times the log of whatever that value is, and then that's how you get this value here. Okay, so what else can you do? And that's an example here. Often, so an amplifier is what's known as an analog circuit, and a digital circuit is an example here that I show you as a ring oscillator. And what I want to show you here is, first of all, in order for these devices to operate and work, as you can see here, they get this sort of oscillation in the current. That means it's kind of ringing, and I'm going to describe why in a second. But I just want to say, from a standpoint of our community working on nanocrystals, is that this is really big, right? And in order for it to work, all the devices have to have the same characteristics. And so it's just a measure of the advances in our community to make very uniform performing materials and devices. And so in this example here of a ring oscillator, we have 10 transistors. It's known as a 5-stage ring oscillator because you need 2 for every stage. So this 2 are the inverters. And so if you have 5 inverters, that's made as a ring. And then there's one more stage that serves as a buffer to the electronics on the output. But I really want to focus on these 5 here to describe to you how the ring oscillator works. So for example, we said, look, this is where it's operating as a switch, right? There's 2 extremes where a low voltage in will give you a high voltage out. So if I put on the input a low voltage, as you see here with this red L, what I should expect is that the inverter will give me a high voltage out. That high voltage out will now become the input of the next one. So you should expect a low voltage back out of the next one. So watch what happens. That if I have a low voltage in, you get high, low, right? So that low voltage in drives this one to be high, which is now the input of the next, which brings a low voltage out, which makes the next one high, the next one low, the next one high. Now that high can then be read out here by this circuit, or what happens is that these are also tied together And that high comes around this wiring and becomes the input now of the next cycle of this ring oscillator. So now if that it becomes high, then its next one is going to switch and this next one is going to become low. And so what happens is that by choosing an odd number of inverters, you get this ringing behavior because you're alternating between whether the signal out is high and low. And that's what you see here. It's high, it's low, it's high, it's low. And that's how a ring oscillator works. And the faster that this time scale is, it gives you a way to measure how fast your transistors are that are contributing to your circuit. So you might notice that this says milliseconds, which is kind of slow. So what was the important characteristic? It keeps going. The important characteristic was for us to learn how to get past using shadow masks and brute force and working entirely in a glove box. And so we did that by discovering that if we looked at our nice transistors built in the glove box, gave us this nice blue curve here. But if we exposed them to air, we would get this green curve here, which basically looks bad, right? And what we learned from that is that, and I won't go through these in detail, but we used electrochemical measurements. And you could see that what was happening is that oxygen was creating a defect state in the material that would kind of grow in as we expose it more and more to oxygen. But what we had realized is that if we re-annealed the device, we could bring back the characteristics here to the black curve. And so you can see that we have our device. If we expose it to air, this current level here starts dropping. That's what we're mapping. And then it depends a little bit on which oxide surface we built our transistor on. If we anneal it, it comes back. We expose it, it gets bad. We re-anneal it, it comes back. And so you could do this over and over. And what we learned through analytical measurements is that as we anneal, the indium from the electrodes would go in and sort of getter and fill these defect states. If you anneal without indium, that defect states stay. And so it becomes actually much more stable over time. And so there are two key things is that the influence of things like air, which has oxygen and moisture, also affects this interface trap density here between the two. And so annealing drives out the oxygen and the water. And then we can also sort of repair the nanocrystals. So these surfaces are both very important to device operation, but it meant that we had a way to go in and make these devices, take them out of the glove box and then repair them. And so then we could use conventional clean room fabrication. So this is a 4-inch silicon wafer. We can spin coat these exchange nanocrystals. This is 144 transistors. We could follow them. They were all quite uniform in making high mobility devices. We could use ALD encapsulation to protect these devices and maintain their stability. And you can just see we can make high mobility devices that just wouldn't change in mobility or threshold voltage over time. And so we followed them for a couple of months. So then we went back and said, if we can do that, photolithography gives us much smaller dimensions. And so we could remove some of these parasitic effects of capacitances and basically revisit the idea that we could make, this is again showing the source and drain, and we developed a via process, which is actually harder than it looks, to cut through to the gate electrode. But this is now our next inverter, which we now have to look at under a microscope instead of by eye, fortunately. And then this is the ring oscillator. And you could see now that we could now have these devices operate to much higher voltages and much higher speeds. Now we're in microseconds. So we could make much better amplifiers and ring oscillators as examples of both analog and digital electronics. If we look at how fast, so if they're really fast, the delay should be small. And we also want devices to operate at low voltage. So we always want to push into this bottom left-hand corner. So this is nanocrystal transistors shown in yellow stars. And the other green, anything that's open was built on plastic. Anything that was not open, that's filled, it was built on a solid substrate, often silicon. But you can see that organic devices are up here in green. As much as I like these materials, they don't perform as well as the nanocrystals. And we see that now these compete with things like indium, gallium, zinc oxide deposited by solution methods and carbon nanotube arrays. And so we could go, I'll skip this as well. We could start making more complicated logic circuits. I know that we're about there, but I'll just say, we can also think about how we build all of these devices now and think towards manufacturing and solution-based materials. So everything I told you about, for example, cadmium selenide nanocrystals to form the nanocrystal layer, we've done very similar things with metals. And so you can use them to take metal particles and use the same kind of ligand exchange processes to make high conductivity metals. We also developed a process sort of layer upon layer to build good low leakage gate insulators. And so we could build transistors entirely from particle systems. In this case, we also had to develop a way for doping. And since we didn't want to use evaporation, we made colloidal indium and introduced them into the source and drain electrodes. And they similarly acted as a source of atomic indium to dope the cadmium selenide channel. But we could do this and then use lithography to pattern, for example, the gate electrode. We could develop this process to deposit the insulator, deposit the semiconductor, use lithography, deposit the source and drain electrodes. And so these examples here are transistors entirely built from particles. And everybody here presumably has sufficient interest in nanocrystals to appreciate that. I won't go through the characteristics individually, but just show that we could reproduce these devices had mobilities of about 20 centimeters squared per volt second, but were entirely processed from nanocrystals. So I'm going to skip all of the other material. I'm going to skip just down to just to tell you we can do the same kinds of things with materials like copper indium diselenide. We started to, I know I appreciated the question of similarly being interested in removing some of the cadmium and the lead. So you can do those, for example, make some of these same kind of devices. We actually started with the thiocyanate exchange cadmium selenide, and learning from our colleagues like Liberetto on cation exchange, we use these kind of approaches to make copper indium diselenide, and so we can start to get mobilities that are high on the order of about 10 centimeters squared per volt second. So we're starting to try and work to get these materials to work better. And I'll skip the examples and just of these fused materials, but tell you that you can do those as well and get higher mobilities now of even about 35 centimeters squared per volt second. And also say that the Tolapin group did some very nice work on using these as precursor materials to make polycrystalline films that now have really nice mobilities even compared to most polycrystalline films by choosing ligands and creating this kind of molecular solder where they're getting mobilities of above 200 centimeters squared per volt second. So I think there's quite some opportunities for nanocrystal materials and electronics, and the opportunity to look at them in integrating them into electronic circuits.